Okay, thank you.
Thank you too.
So I'm Andrea Pisarda. I'm a professor at University of Catania at the Department of Physics and Astronomy. And I will present this study that was published this year. This study is about acoustic emission in compression of building materials. And we applied Q-statistics in order to anticipate the breakdown point. So this is our team, composed mainly by colleagues, engineers of our university, Annalisa Greco, Andrea, myself, of course, Alessandro Pluchino, Gabriele Fichera, and Loredana Contraffatto, in collaboration with Costantino Zallis from Rio de Janeiro. Okay, let's see what we have done. We have studied acoustic emission testing measured in several materials, brittle materials, which were compressed. Usually when materials are compressed, they emit this localized stress energy, which propagate as an elastic wave. And if you put some sensors, you can record these acoustic emissions. And the hope is just to predict several statistical features which enables to predict the breakdown point. The materials that we have studied are concrete and basalt. And we applied several cyclic compressions until the breakdown point. So let's see the kind of materials. The first one is concrete, which is an artificial conglomerate, which consists of cement, water, and sand and gravel within a certain appropriate recipe. And it was prepared 28 days before the test in order to allow some hardening of the material. The second one is a very common rock that we have here in Sicily, living below mountain volcano, and it's basalt. So when magma comes out, it cools down and when it is in contact with the atmospheres, and this stops the crystallization process. And we have a very compact structure of these rocks, which have a very excellent resistance to mechanical stresses. Okay, so this is our experimental setup. We have an hydraulic press, which is connected to a data acquisition unit. You may see here in the middle just the hydraulic press, then the acquisition unit, and just in the middle you see the specimen of concrete, in this case, which was coupled with the acquisition system through a piezotron acoustic emission sensor. This is another picture of this press and the two specimens after the breakdown point. What we have done is we have applied some cyclic compressions, and first of all we observed the so-called Kaiser effect. That is, the material emits these acoustic emissions only if you increase the compression after a certain point. Then you release the compression and you start again, but the acoustic emission starts again when the load overcomes the previous one. So we did this for the two kind of materials, concrete and basalt, and these are the plots for two samples. And then we studied the inter-event time, delta tau, in order to see the kinds of statistics that we obtain. Here on the left, you see concrete, and on the right, basalt. And this is just the last nodding before the breakdown. And you see that the acoustic emission are clustered, and the inter-event time shows a very nice distribution, a power law distribution, which has a slope which in the case of concrete is -1.6, And in the case of basalt is minus 1.9. So this shows that we have a kind of complex behavior just before the breakdown point. Then we studied the complementary cumulative distribution function for these inter-event times. That is the fraction of inter-event times greater than a certain value, delta tau. These are reported on the right for the two samples of concrete and the two samples of basalt. As you can see, you can fit very well this behavior with a decreasing Q exponential, which is indicated here on the left. And this function has two parameters, Q and beta Q, which is an inverse effective temperature, TQ. And this is the kind of function which maximizes the Q entropy, which is the generalization of entropy, or the Boltzmann-Gibbs entropy, when you have correlations in your system. In fact, Q, the entropic index Q, is considered a measure of strong correlation in the system. When Q is equal 1, you have no correlations. As you see, in our case, Q is greater than 1 in all cases. And TQ can be considered an effective temperature, which indicates the level of noise that you have in your system, in your process or fracturing process. So we reported then the values that we have obtained in this plot, where you observe for the different samples and the different materials. We had two samples for the two different materials that we studied, basalt and concrete, and you see a different behavior. So we think they belong to two universality classes. And in any case, when you approach the breakdown point, which is when you go from C to B and then to A is just the last loading, B is the second to last loading, and C is the third to last loading. You see in the case of concrete that there is a decreasing behavior of Q, but the effective temperature goes to 0, while in the case of basalt, you see that an increasing trend in the value of Q, and also in this case, going towards the breakdown point, the temperature goes to 0. Then we compared also this measure that we did with some data that came from this other paper here on the bottom. It's a paper by a Greek group that studied a similar material within a similar experiment. It's not exactly the same. It's white mortar, but it's also a conglomerate material similar to concrete. And you see that the trend is similar to our case of concrete, although the values of Q are slightly less than the one we obtained. So to conclude, we have observed two different behavior for the two materials that we have studied, concrete and basalt. And this is because concrete is a composite material. So you can see that the cracking evolves along some mesoscopic preferential lines that you observe also with your eye, and which form this long-range correlation that increase the value of Q. On the other hand, the dynamics of the breakdown for basalt is quite different, since basalt is a material which is much more compact and homogeneous and breaks down almost immediately because it resists to strong compressions in a kind of explosive way. We think that if this test will be confirmed in future experiments that we are analyzing, this could be very useful in order to predict within a kind of health monitoring strategy, non-destructive, the conditions of very big buildings and bridges in order to predict to anticipate, let's say, the breakdown point and to avoid problems. So this is the end. I thank you for your attention. This is our group, and I'm here for your questions, if there are. Thank you very much.
Thank you very much for your very interesting talk, Professor Rebisate. And do you have any questions for this interesting talk? I don't see any question. Okay.
Okay.
That was very interesting. And I'm wondering how, if is relating this entropic parameter with the number of cracks in a, for example, say in a metal. Let's take a metal structure, and there is a entropy, for example, of cracking in metals, and this is relating with the cracks. Do you have to comment on this? If it's a similarity with the concrete materials?
And actually, I don't know. Are you referring to some published paper?
Yes, I'm referring to a lot of work which relates in metals, the number of cracking, of micro cracks or nano cracks, with the entropy of a system. And actually, I'm wondering if is this parameter, this Q parameter, in this application is related as well with the number of cracks.
Okay, I actually don't know about these papers, but I would be very much interested in that. If you can provide me the literature, I'm very much interested, because this was our first test, our first study in this direction. So we knew this study by the Greek group, I didn't know any other connections of this kind with the Q statistics. So I would be very much interested in reading these papers.
Okay, thank you very much indeed. I will try to find them and just communicate.
Okay, thank you. Thank you very much.
Thank you. Okay, and with this last talk, I think we have to end the session. I thank you, all of you. I hope you are safe in these difficult times. And let all of us try to do our best. Thank you very much.
Thank you. Have a nice evening.
Bye-bye.
Thank you very much, Kostas.
Bye-bye.
Thank you. Thank you.
Thank you all.